This video covers a couple of practical ideas with regard to measuring voltages. Here's an old battery. I'm going to use a voltmeter to measure the voltage between the two ends of the battery. So we see that it has a voltage of 8.84 volts. I'm going to use this battery together with a resistor in a simple circuit. I've measured the resistance to be 176 ohms. Here's the simple circuit that we're going to be using. We've got a complete loop so that current is going to flow from the battery through the resistor. And I'm going to measure the voltage that appears on the battery as we let current flow. Now we see that the voltage on the battery is dropped to about 8.18 volts. Why is that? We're asking the battery to do work, namely drive current through the resistor. That's going to cost some energy. This happens to be an old battery and there's not much power left in it. How much power were we expecting? Well, power is the product of the current and the voltage. So what current level were we expecting? I'm using Ohm's law here to calculate the current as the voltage over the resistance. So the voltage that we're applying is 8.84, and we have a resistor of 175 ohms. And that gives a current of 0.0505 amps. The power that we should expect is the product of this current and the voltage 8.84 volts, or 0.446 watts. Let's calculate the power that was actually observed. We can get that from the current times the voltage, but in this case it would probably be easier to take the voltage divided by R for the current and multiply by the voltage, or get voltage squared over R is the power. That's the voltage of 8.18 volts squared divided by resistance of 175 ohms. Or that's 0.382 watts. Whenever we put a battery or a voltage source in a circuit, we're asking it to provide current and do work. We say that it's under a load. In this particular case, we asked more of the battery than it could provide, and so it dropped its voltage to provide the current. If the total resistance is large, the current that the source needs to provide is small, and the load is not very heavy. We almost always want to avoid loading the source beyond its ability to provide current at the expected voltage. Otherwise, the voltage will drop from the source's unloaded value. Loading is also an issue when the voltage source is a signal from an instrument. We want to avoid drawing much current from the source so that we don't distort the signal. We've been using a voltmeter to measure voltages in our demonstrations, assuming that we are not distorting the system, but we should examine this. When we attach the voltmeter, it becomes part of the circuit. If it draws much current, an error results. But how much is too much? Some people are happy as long as their errors are 1% or less. I generally prefer to keep errors on the order of 0.1% or less. Let's take a look at that. Here I'm using a new battery with a voltage divider. Here I've got a voltage of 1.557 volts. Both resistors are essentially 1 million ohms. Since they are in series, the same current will go through both resistors, and we can calculate that from Ohm's law. That will be equal to the voltage divided by the sum of the resistors. Here we have 1.557 volts divided by 1.009 plus 1.011 times 10 to the 6th ohms. That gives us a current of 0.770 times 10 to the minus 6 amps, or 0.77 microamps. Let's imagine we want the voltage across RB. You might want to pause the video and try that calculation for yourself. Here's what I get. The current of about 0.7 microamps times 1 million ohms is 0.770 volts. Let's connect the voltmeter and take a look. Let's move the test lead to the junction between the two resistors. Whoa, that's much less than we predicted. What's wrong? We predicted about 0.77 volts, but we observed only 0.517 volts. Notice that when we did our calculations with the voltage divider, we ignored the voltmeter. We were assuming that all of the current coming from the top of the resistor went through the bottom resistor and no current went through the meter. The meter does actually draw a tiny current. It depends upon the quality of the meter, but it's typically around 0.1 to 1 microamp. That's not very much, but in this case it's on the same order of magnitude as the current that should be going through resistor RB. Therefore, we are loading the signal that we are trying to measure. This is causing an error. In this case, the relative error is rather large. If we calculate the percent error as the discrepancy between the theoretical and the observed voltage compared to the theoretical voltage, it's about 33%. Another way of looking at this issue is to realize that the meter has some effective resistance, and it's called the input resistance of the meter. Let's redraw the circuit to represent the meter as though it were another resistor, Rm, in parallel with the bottom resistor. The voltage that we want to measure is that appears here at the junction of these resistors. So our voltage divider now includes this pair of resistors RB and Rm parallel with each other. The combination will have the product over the sum of the resistance for that value, and the total current in the loop will be the sum of this parallel resistance, whatever its value is, plus RA. The current in the main loop then will be the total voltage, 1.557 volts for our battery, divided by the total resistance that is indicated above. The measured voltage will be the current times the resistance of this parallel combination. And when we expand that, it looks rather involved. But we can see some special cases here. We know that in our particular case that RA and RB are equal to each other. And what if RA and RB also equal Rm? In that case, the parallel resistance works out to be essentially 1/2 of RB. And the total resistance, the term in our denominator, just becomes 1.5 RB. So the voltage that we measure should be 1/3 of the total voltage, or the battery voltage. In our case, that's 1.557 volts divided by 3, or approximately 0.519 volts. And that's remarkably similar to what we actually observed. This implies that our resistance for our meter is actually about 1 million ohms. An important take-home message is when Rm is much greater than Rb, the resistance is essentially that of Rb. So loading errors are negligible. So loading errors will be negligible if Rm is at least 1,000 times bigger than Rb.